Hi, everybody. Class 70, we're going to get into the Doppler effect a little bit, and one of its applications is the sonic boom. So, just a couple things to review. If a wave does not change a medium, its speed remains constant. But within a given medium, if the wavelength were to increase, the frequency has to go down. And vice versa. Within a given medium, if the wavelength were to decrease, the frequency has to go up. Just to remember that as we talk about the Doppler effect. So, it's a quick little video, check it out. But basically, what you realize was that the frequency of the fire truck was higher as it approached us, but lower when it went away from us. That is the Doppler effect, how the frequency changes when something is moving relative to you. There's a really good simulation here. Check it out, play with it a little bit, and just make sure you're familiar with what it is, because I'm going to refer to it a lot. So what you should have noticed in the simulation that as an object emitting noise approaches you, you hear a higher frequency because the wavelengths get shorter. Okay, if you notice in the simulation, in the direction the object was moving, the wavelengths bunched together closer. When it was moving away from you or away from the observer, the frequency got lower because the waves spread out more. So check that out in the simulation. Make sure you recognize that in the direction the object is going, the waves bunch up, and away from it, the direction it's not going, the waves spread out. That's why the frequency and the wavelength change. Now, let's switch it up. Let's say the observer is approaching the stationary object. They're going to hear a high frequency still because the wavelengths they perceive are going to be shorter. They're going to reach each successive wave crest quicker. So it's going to appear as if the wave is shorter. If you're going away from a stationary observer, you're going to hear a lower frequency because the wavelength gets longer because you're kind of running away from the wave as it's coming toward you. Notice that numbers 1 and 3 are very similar. When objects are getting closer to each other, the frequency is higher. Look at numbers 2 and 4. When objects are moving away from one another, the frequencies get lower. So this is a really good video that summed up the Doppler effect. Check it out. It's summed up in your own words, but it should be something to this effect. When two objects are moving toward each other, doesn't matter which one's moving, as long as one of them is moving, the frequencies that the listener perceives is going to be higher. If two objects move away from each other, the frequency that the observer perceives is going to be lower. The frequency that's emitted is never going to change. So one really important thing is that the Doppler effect has nothing to do with the volume you hear. But a lot of people think it does. Why? Because in general, when objects get closer to you, they get louder. Okay, that's not because of the Doppler effect, that's just how volume works. The Doppler effect is just the change in frequency. It has nothing to do with the change in volume. So a sonic boom, what is it? Well, a sonic boom is a really nice application of the Doppler effect. All right. So if you play with the simulation and set the speed to 1, which means 1 times the speed of sound, you see something pretty cool. You see all the waves line up. So what's going on there? So when you're traveling, or when an object is traveling at the speed of sound, all the waves line up perfectly, which results in constructive interference. This constructive interference, think about it, when a bunch of waves come together constructively, create one giant sound wave, the boom. Okay. Now, the boom is not a one-time event. It follows the airplane as it moves. So everyone's going to hear the boom at some point as long as the airplane passes you. So think about this, though. This is not quite what sound waves look like. Picture all of these sound waves, all these waves lined up because the Doppler effect forced them all together. What's the result? One giant wave of sound. Okay. So the Doppler effect is a really nice combination of both the sonic boom is a really nice combination of both the Doppler effect and the and constructive interference, excuse me. All right, this is a classic Doppler effect question. Basically, it's saying that compared to the frequency of the sound of the horn heard by driver B, that's like the person emitting sound, the frequency heard by person A is going to be lower, right? Because the car's moving away from them. But C is going to hear a higher frequency because it's moving toward them. Now, this one's a little bit more difficult because I think of the graph. So a car is approaching, passing, and moving away from a stationary observer. We have to think about the frequency that the stationary observer hears. Okay. So as it approaches, they hear a higher frequency. When it passes them, they hear the true frequency. When it moves away, they hear a lower frequency. So we know that as time goes on, the frequency has to go from a higher number to a lower number. That's why we eliminated choices 1 and 4. So how do you differentiate 2 and 3? Well, there is something that the simulation shows you, but it's really important. When the object emitting sound is approaching the observer, we hear a higher frequency, but it's a constant higher frequency. It's not like constantly, it's not higher and getting lower gradually. It's a higher number. And then once it passes them, it's a lower number. So this is actually what it looks like. This is kind of the reason why we don't use a Doppler effect equation, because it's not a normal function. It is a constant number as it approaches, and is a different constant number as it moves away. So I wrote something down here just to help you out and to word this to yourself. As the car approaches, the observer hears a higher constant frequency. It's not constantly getting higher, it's not getting louder and then softer, it's a constant higher number. Then as the car moves away, the observer hears a constant lower frequency. All right, just one low frequency. There's only like an instant in time when the observer hears the true frequency, like that moment the car is just in line with it as it passes it. Okay, so that's why it's number 3, not number 2.